Our universe exists on a knife edge of impossible precision. The strength of gravity, the mass of an electron, the expansion rate of space itself, these are not arbitrary numbers. They are the universe's fundamental constants, the unchanging settings that make reality possible. Alter any one of them by even a minuscule fraction, and stars would not shine, atoms would not hold together, and life could never arise. This is the mystery of cosmic fine-tuning. By the end of this journey, you will understand the staggering evidence that our cosmos appears exquisitely engineered for existence, and you will confront the ultimate interpretations that could redefine reality. How did carbon, the element of life, come to exist through a seemingly perfect nuclear resonance? Why does empty space contain exactly the right amount of dark energy to allow galaxies to form? The physicist Freeman Dyson once reflected that the universe, in some sense, must have known we were coming. So what does this profound alignment mean for us? Is it the signature of a deeper design or the ultimate cosmic accident? The answer depends on where you draw the line between physics and philosophy. What kind of universe feels most true to you? Every single atom in your body, every star in the sky, is governed by a set of unchangeable numbers. These are the fundamental constants, the universe's deepest settings. Think of them as the control knobs on a cosmic machine. There is a knob for the strength of gravity, another for the force that holds atomic nuclei together, and one for the energy density of empty space itself. These numbers are not predicted by any theory. They are simply measured, and they are shockingly precise. They form the bedrock of all physical law, the rules of the game that matter and energy must follow. And here is the profound mystery. These numerical settings appear to be perfectly dialed in for the existence of complex life. If the gravitational constant were a little higher, stars would burn out in a cosmic blink. If the electromagnetic force were a little weaker, atoms could not bond to form molecules. The universe would be a vast, dark, and sterile expanse. This is not about life finding a niche in a harsh cosmos. This is about the cosmos itself providing the only possible niche for life to even be conceivable. The precision required is beyond human comprehension, like a master watchmaker adjusting a clock's gears to within a billionth of a millimeter, not once, but for dozens of interdependent settings simultaneously. This delicate balance is the very heart of the fine-tuning argument. It suggests that out of all the possible universes that could exist with different random settings, we find ourselves in one that is almost impossibly hospitable. It is the first and most compelling clue that our reality might be a very special place in a vast landscape of silent, lifeless possibilities. Gravity is the force that sculpts the cosmos, the silent architect of galaxies and stars. Yet its strength is not a given, it is a specific number, a constant we call capital G. To appreciate its fine-tuning, we need to adjust that number ever so slightly in our minds. Picture a universe where gravity is just 1% stronger. This tiny change would have catastrophic consequences. Stars, under that increased pull, would burn hotter and faster. Their nuclear furnaces would rage with such intensity that they would exhaust their fuel in mere millions of years, not the billions our sun enjoys. They would then collapse, likely into black holes, before any stable planetary systems could coalesce, let alone before life could emerge and evolve on a world like Earth. The universe would be a fleeting spectacle of brilliant, short-lived stars, followed by an eternity of darkness. Now consider the opposite. If gravity were even a fraction weaker, the gentle attraction between particles of dust and gas in the early universe would be insufficient. Matter would never gather into the dense clouds needed to ignite stars. The cosmos would remain a thin, cold, and perpetual haze of hydrogen and helium, with no galaxies, no light, and no chemistry beyond the simplest elements. Cosmologist Martin Rees captured this perfectly when he identified the strength of gravity as one of his famous 6 numbers that shape the universe. He noted that this force is balanced on a knife's edge. It is strong enough to pull the universe together into interesting structures, but weak enough to allow those structures to evolve slowly and steadily. This precise calibration gives us a stable stage. It allows for long-lived stars that can warm planets for eons. It provides stable orbits so a planet's climate isn't thrown into chaos by a wandering star. This stability is the non-negotiable foundation for the gradual, intricate process of evolution. Without gravity being exactly what it is, the chain of events leading from the Big Bang to a thinking being gazing at the stars would have been broken at its very first link. So when we feel the steady pull holding us to the ground, we are experiencing not just a law of physics, but a cosmic prerequisite, a force tuned with unbelievable precision to make our existence possible. The vacuum of space is not truly empty. It hums with a faint, repulsive energy, a force woven into the fabric of reality itself. This is dark energy, and its discovery overturned our deepest assumptions about the cosmos. For most of scientific history, we believed the universe's expansion, born from the Big Bang, was gradually slowing down under gravity's relentless pull. Then, in the late 1990s, astronomers made a shocking observation. The expansion of the universe is not slowing, it is accelerating. Something is pushing galaxies apart from one another with ever-increasing force. That something is the energy inherent to empty space, described mathematically by what Einstein once called his greatest blunder, the cosmological constant. The sheer weakness of this force is what makes its tuning so breathtaking. Dark energy's repulsive push is unfathomably feeble. If you gathered all the dark energy within our entire solar system, its total strength would be less than that of a small battery. Yet, across the vast distances between galaxies, this tiny effect dominates gravity and dictates the ultimate fate of everything. Now, consider the knife's edge. If the value of this cosmological constant, this energy of the vacuum, were just slightly stronger, the acceleration would have begun almost immediately after the Big Bang. Matter would never have had a chance to coalesce. Proto-galactic clouds would have been torn apart before stars could ever ignite. The universe would be a cold, thin, and lonely void, expanding into oblivion with nothing in it. Conversely, if dark energy were even a tiny bit weaker, gravity's attractive force would have won out long ago. The cosmos would have reached a maximum size and then collapsed back in on itself in a catastrophic reversal of the Big Bang, an event scientists call the Big Crunch. All structure, all potential for life would have been erased in that fiery contraction. For a universe to be life-permitting, this constant must be balanced with almost impossible precision. Physicists calculate that its value is fine-tuned to around 1 part in 10 to the power of 120. To put that number into perspective, it is more likely to win the biggest lottery jackpot every single week of your life for millions of years than for a universe to randomly land a cosmological constant in the life-allowing range. This is not a minor adjustment. It is like balancing a pencil on its tip for billions of years, a feat of stability so exact it defies belief. The philosophical weight of this discovery is immense. We are forced to ask, why does nothingness have exactly this property? Why does empty space possess this specific, minuscule amount of repulsive energy, a value that seems meticulously chosen to allow for galaxies, stars, planets, and ultimately, us? The vacuum could have had zero energy. It could have had an enormous amount. Instead, it holds this precise, golden number, making the silent void not an empty stage, but an active and finely tuned participant in the story of our existence. Deep within the heart of a star, a cosmic forge operates under unimaginable pressure and heat. This is where the universe cooks the raw ingredients for everything you see around you, from the iron in your blood to the calcium in your bones. The master chefs in this kitchen are two fundamental forces working in a delicate and precise partnership. The strong nuclear force is the ultimate glue. It is what binds protons and neutrons together in the atomic nucleus, overcoming the powerful electrical repulsion between positively charged protons. Without it, no complex atomic nuclei could ever form. Hydrogen, the simplest atom with just one proton, would be the only element in existence. There would be no stars, no planets, and certainly no chemistry of life. The strong force's strength is set on a very narrow ledge. If it were just a few percent stronger, protons would bind together so readily that all the hydrogen in the early universe would have fused into heavier elements almost instantly. Primary fuel for stars would have been exhausted before the first star ever flickered to life. Conversely, if it were slightly weaker, protons could not stick together at all. The universe would remain a featureless soup of hydrogen, unable to light the nuclear fires that power stars. The other chef, the weak nuclear force, operates more subtly. It governs certain types of radioactive decay, a process crucial for the life cycle of stars. When a massive star reaches the end of its life, it does not fade quietly. It explodes in a cataclysmic supernova, an event of staggering violence that seeds the galaxy with heavy elements. This spectacular dispersal is orchestrated by the weak force. As the star's core collapses, the weak force enables neutrons to form, which then allows for the rapid creation of elements heavier than iron. If the weak force were significantly stronger, the process that builds these elements inside the star might not happen correctly. The star could collapse directly into a black hole without the brilliant element-scattering explosion. If it were much weaker, the necessary reactions might not occur at all, leaving the universe devoid of many essential metals. Think of it as a recipe with exact cooking times and temperatures. The strong force sets the heat of the oven, allowing the nuclear fusion of helium and carbon. The weak force acts as the timer, determining when the star's core becomes unstable and triggers the supernova that plates the finished dish across the cosmos. This is not a single, isolated fine-tuning. It is a chain of interdependent miracles. The precise values of these forces allow for long-lived, stable stars that cook helium into carbon and oxygen. Then they enable the violent, beautiful death of those stars, which packages those elements and flings them into interstellar space. Those ejected elements later coalesce into new solar systems, rocky planets, and eventually the molecules of life. The carbon in every cell of your body was forged in such a stellar furnace and delivered by such an explosion. This reveals a profound truth about the fine-tuning argument. It is not about one lucky dial setting on a cosmic control panel. It is about a symphony of constants, each perfectly tuned not only in isolation, but in harmony with all the others, composing a universe capable of building complexity from simplicity and life from stardust. So if the universe is so perfectly arranged, who or what arranged it? A compelling answer emerged not from theology, but from the logic of science itself. It is called the Anthropic Principle. At its core, it is a simple, almost tautological statement. We observe the universe to have properties that allow for our existence, because if it did not, we would not be here to observe it. This is not an explanation for why the constants are tuned, but rather an observation about our inevitable perspective. Imagine you are a fish that has only ever lived in a freshwater pond. You might marvel at how perfectly the water's chemistry is suited to your gills, its temperature ideal for your biology. You might conclude the pond was engineered just for you. But the wider reality is that there are countless bodies of water, some salty, some acidic, some frozen solid. You simply find yourself in the one pond you can survive in. The Anthropic Principle suggests we are that fish, and our universe is that pond. Our presence acts as a powerful filter on what we can possibly see. We could never find ourselves in a universe where gravity is too strong for stars or where atoms cannot form. Those dead universes exist only as theoretical possibilities, unobserved and empty. This idea gains real traction when paired with the concept of a multiverse. Physicists like Leonard Susskind propose that if our cosmos is just one bubble in a vast, frothing sea of universes, each with its own random set of physical laws, then our incredible luck is no longer surprising. In an infinite array of possibilities, every possible combination of constants will be realized somewhere. Most of those bubbles will be stillborn, dark, or chaotic. But a tiny fraction, by pure chance, will have the right numbers for stars, planets, and life. We, of course, must find ourselves in one of those rare, habitable bubbles. It is a cosmic version of winning the lottery. Someone always wins, and the winner is naturally astonished. The Anthropic Principle, in this view, offers a naturalistic solution. It removes the need for a cosmic engineer by invoking sheer, mind-boggling multiplicity. Yet this leads to a profound and unsettling question. Does this principle truly solve the mystery, or does it merely relocate it? Instead of asking why our one universe is so fine-tuned, we are now asked to believe in an unimaginably vast and complex multiverse, whose own underlying laws must still permit such endless bubble universes to exist. The tuning problem shifts from the constants of physics to the laws that allow a multiverse to generate them. Some argue this is not an explanation, but an infinite retreat. Are we explaining the remarkable, or simply hiding it behind a curtain of even greater remarkable things? The principle forces us to confront the limits of our own reasoning, standing as a crucial and deeply controversial counterweight to the intuition of design. This cosmic lottery needs a place to happen. The multiverse hypothesis provides the ultimate venue. Think of reality not as a single stage, but as an endless, bubbling expanse of cosmic foam. Each bubble is a separate universe, inflating into existence with its own unique, random set of physical laws and constants. In most of these bubbles, the numbers are all wrong. Gravity is too strong and everything collapses instantly. The nuclear forces are too weak and no atoms ever form. These are dead universes, dark and empty. But in a staggeringly rare few bubbles, purely by chance, the numbers fall within that razor-thin life-permitting range. We inevitably find ourselves in one of those lucky bubbles. This is not mere philosophy. Some of our most advanced physical theories, like eternal inflation and string theory, naturally suggest such a landscape. Eternal inflation proposes that the rapid expansion of space during the Big Bang never truly stopped overall, but instead continues eternally, spawning new bubble universes like a ceaseless fountain. String theory, a candidate for a theory of everything, suggests there may be an astronomical number of possible stable configurations for the extra dimensions it proposes, each configuration corresponding to a different universe with different physics. This gives the multiverse a potential mathematical foundation. It offers an elegant, if overwhelming, solution to fine-tuning. No designer is needed, just the relentless, random churn of cosmic probability across an infinite canvas. Yet here we encounter a profound tension. For all its theoretical appeal, the multiverse, by its very nature, may lie permanently beyond our observational reach. If other universes are causally disconnected from our own, with no possible exchange of light or information, how could we ever test their existence? This leads many critics to argue that the multiverse is not science, but metaphysics dressed in mathematical equations. It becomes a philosophical escape hatch, a way to explain away the astonishing specialness of our universe by invoking an even more astonishing and unverifiable reality behind it. The question then becomes, are we looking at a groundbreaking expansion of scientific thought, or a sophisticated retreat from a mystery we are not yet ready to solve? The equations and probabilities we have been discussing lead us to a crossroads far older than modern science. The evidence for fine-tuning does not speak for itself. It whispers a question, and how we answer it depends less on the data and more on the philosophical framework we bring to it. Logically, we are presented with a trilemma, three broad paths to explain why the universe appears so perfectly set for life. The first path is raw, staggering coincidence. On this view, we simply won the ultimate cosmic lottery. The philosopher Daniel Dennett might frame this as a brute fact, a singular event so improbable that it defies belief, yet one that must have happened because we are here to remark upon it. This stance requires a monumental leap of faith in chance itself, accepting that against inconceivable odds, every dial just happened to land in the perfect position. The second path is the multiverse, which we have just explored. This attempts to dissolve the improbability by multiplying the tickets in the lottery. If there are an infinite number of universes, then a life-permitting one is not just possible but inevitable. The fine-tuning is then an illusion of perspective, a selection effect in an otherwise barren and chaotic landscape. The third path is some form of cosmic purpose or design. This interpretation suggests the constants are tuned because they were meant to be, that the universe is the product of a mind, a principle, or an intention that values the emergence of life and consciousness. Theologian William Lane Craig argues this point, seeing fine-tuning as powerful evidence for a cosmic designer, a logical inference from the data toward an intelligent cause. Each of these choices shapes reality into a profoundly different story. One is a story of breathtaking, solitary luck. Another is a story of infinite, impersonal churning. The last is a story of intentionality and perhaps even meaning. The challenge for each of us is to ask which story feels most coherent, which framework makes the most sense of not only the numbers but our own lived experience of curiosity, beauty, and reason. This is not about proving one side right, but about understanding the weight of the choice itself and what it says about the universe we believe we inhabit. Yet for all its compelling force, the fine-tuning argument is not a closed case in the halls of science. A significant number of physicists and philosophers raise serious, thoughtful critiques, reminding us that the story is far from settled. One major line of questioning centers on the incompleteness of our knowledge. We are currently working with a patchwork of theories, general relativity for the very large, quantum mechanics for the very small. The dream of a final theory of everything, a single elegant framework from which all forces and constants naturally flow, remains just that, a dream. But if such a theory were discovered, it could completely reshape the problem. Perhaps the constants we see are not freely adjustable knobs at all, but the only possible outcomes of a deeper, more fundamental law. In this view, the universe could not have been any other way, making the idea of tuning irrelevant. The apparent fine-tuning would be a mirage, a consequence of our still limited understanding, waiting to be dissolved by a future Einstein. Another critique challenges the very definition of life permitting. Our imagination is necessarily constrained by the single example of life we know, carbon-based, water-dependent, existing within a very narrow band of physical conditions. But who is to say life could not be unimaginably different? Perhaps in a universe with a stronger nuclear force, complex structures could form from nuclei alone. In a cosmos without stable atoms, patterns of energy in plasma might achieve a form of consciousness. The physicist Victor Stenger was a prominent voice here, arguing that we have a sample size of one, and it is premature to conclude that our specific recipe is the only one on the cosmic menu. He contended that fine-tuning is an illusion born of our tendency to work backwards from the result we see, rather than forwards from the laws of physics. We assume the constants are independent and freely variable, then marvel at the odds against our existence. without proving that other sets of constants couldn't lead to some other, equally fascinating form of complexity. Furthermore, some researchers point to the sheer vastness and apparent waste of our own universe. If it were so finely tuned for life, why is the overwhelming majority of it utterly lethal to us, a vacuum filled with radiation and scattered, frozen rocks? This perspective suggests that life is not the goal of the cosmos, but a rare and fragile accident within a largely inhospitable reality. The debate, therefore, remains vibrantly alive. It is a dialogue between awe at the numbers and caution about their interpretation, a necessary tension that drives science forward. Long before we had equations to describe the gravitational constant, humanity gazed at the heavens and sensed an underlying order. This intuition of a cosmos arranged with purpose is not a modern invention, but a thread woven through the entire tapestry of human thought. In ancient Greece, Plato envisioned a divine craftsman, the demiurge, who shaped the chaotic raw materials of existence into an orderly cosmos reflecting perfect, eternal forms. This was not a story of creation from nothing, but of imposing a rational, mathematical blueprint onto primordial chaos. The universe, for Plato and many who followed, was inherently intelligible because it was the product of a rational mind. Centuries later, at the dawn of modern science, Isaac Newton uncovered the precise mathematical laws governing motion and gravity. To him and his contemporaries, this breathtakingly precise clockwork universe was the clearest possible evidence of a supreme clockmaker. The laws themselves were seen as divine decrees, the consistent rules set by a creator for the cosmos to follow. Science, in this view, was the process of uncovering the mind of God through the language of mathematics. The universe was a book to be read, written in geometric characters. This harmony between scientific pursuit and theological wonder defined an era. The pivotal shift arrived in the 20th century with the discovery of the Big Bang. We learn the universe had a definite beginning in a hot, dense state, and crucially, that this beginning required incredibly specific conditions to lead to our present reality. The initial expansion rate, the balance of matter and energy, the tiny ripples that would seed galaxies, all of these were set with a precision that stunned physicists. This was no longer a philosophical notion of general order, but a hard, quantitative puzzle written in the cosmic microwave background radiation. The modern fine-tuning problem is the direct descendant of this discovery. It is the ancient question of cosmic purpose, but now armed with data, with numbers stretched across 120 decimal places, with probabilities so small they defy everyday comprehension. Recognizing this long arc is vital. It shows that our current debate is not some new battle between science and belief, but rather the latest chapter in humanity's oldest and most persistent conversation. We have always sought to understand whether the beauty and order we perceive is a happy accident, a necessary truth, or a signature. The tools have evolved from myth to mathematics, but the yearning to find our place within a coherent story remains the same. This historical context humbles us, placing our cutting-edge equations in a lineage of wonder that stretches back to the first time a human looked up at a starry sky and felt a question form in the dark. Carbon is the ink with which the story of life is written. From the graphite in a pencil to the diamonds deep within the earth, from the fuels we burn to the very molecules that make up our bodies, carbon's unique chemistry is the foundation of complexity. Yet this element, so crucial to our existence, should not logically be so abundant in the cosmos. Its creation inside stars is a delicate nuclear ballet that, according to the physics of the 1950s, seemed almost too improbable to account for the world we see. This is where a brilliant and often controversial astronomer, Fred Hoyle, entered the scene with a startling prediction. Hoyle was working to understand how stars forge heavier elements from simpler ones, a process called nucleosynthesis. The path to carbon involved a reaction known as the triple alpha process, where three helium nuclei, called alpha particles, must come together in a star's fiery core to form a single carbon nucleus. The problem was statistical, for three particles to meet simultaneously is incredibly rare. Even if they did, the early calculations suggested the resulting carbon nucleus would be highly unstable and would immediately fall apart before any more carbon could be built upon it. The numbers simply did not add up to produce the abundant carbon necessary for rocky planets and carbon-based life. Hoyle, however, was guided by a powerful, almost philosophical premise. We are here made of carbon. Therefore, the universe must have a way to make carbon in great quantities. He reasoned that there must be a previously unknown resonant energy state within the carbon nucleus itself, a specific, precise energy level that would act like a welcoming catcher's mitt. This resonance would dramatically increase the probability of the triple alpha process, allowing the fleeting trio of helium nuclei to stick together long enough to become stable carbon. To the physics community at the time, this was audacious. A scientist was essentially using the fact of our own existence to predict a specific, measurable property of an atomic nucleus. It was as if a baker, knowing that a cake exists, deduced the exact temperature of an unseen oven. Remarkably, Hoyle persuaded nuclear physicist Willie Fowler to look for this predicted resonance in experiments. Fowler's team did, and they found it. The carbon nucleus possessed exactly the right resonant energy state Hoyle had calculated, a state that seemed tailor-made to facilitate its own creation in stellar furnaces. The implications struck Hoyle with profound force. He later wrote that this discovery shook his atheistic convictions, for it appeared the nuclear laws were not just arbitrary, but curiously biophilic or life-loving. The resonance was not merely a happy accident, but a precise tuning of fundamental forces. If the strong nuclear force which binds atomic nuclei were even slightly stronger or weaker, this perfect resonant energy level would vanish. The triple alpha process would fail, and the universe would be devoid of carbon, and thus devoid of life as we understand it. This story blurs the line between discovery and deduction in a fascinating way. It presents a case where the apparent necessity of life, the fact that we are carbon-based observers, led directly to a breakthrough in fundamental physics. The carbon resonance stands as a powerful exhibit in the fine-tuning argument, suggesting that the universe's laws are not just permissive of life, but seem in some deep sense to anticipate it. It forces us to wonder whether this precise nuclear arrangement is a cosmic coincidence of unimaginable luck or a clue written into the fabric of reality itself. That same carbon chemistry finds its perfect partner in a substance so common we often overlook its strangeness. Water behaves like no other liquid on Earth, and its peculiarities are not minor quirks. They are essential miracles that make our planet a living world. Think of any other substance. When it freezes, it becomes denser and sinks. A lake would freeze solid from the bottom up, entombing any life within it. But water defies this rule. As it cools toward freezing, it does something extraordinary. It expands. This means ice floats, forming an insulating blanket on the surface of lakes and oceans, protecting the liquid water and the life below during long winters. This single anomaly, governed by the unique shape of the water molecule and the angles of its hydrogen bonds, is a foundational requirement for aquatic ecosystems and, by extension, for the climate stability of the entire planet. But the wonders of water do not stop there. It has an astonishingly high heat capacity, meaning it takes a tremendous amount of energy to change its temperature. This is why coastal areas have milder climates than inland regions. The vast oceans act as a planetary thermal battery, absorbing heat during the day and slowly releasing it at night, smoothing out temperature extremes that would otherwise swing violently. Without this buffering effect, continents would bake and freeze with the turning of each day, creating an environment far too harsh for complex life to emerge and thrive. Furthermore, water is the ultimate universal solvent, a property arising from its polar molecular structure. It can dissolve salts, sugars, gases, and a vast array of organic molecules, enabling the intricate chemical reactions of metabolism to occur within every cell of every living thing. Our blood, our sap, our cellular fluids are all aqueous solutions, transporting the building blocks of life to where they are needed. Each of these life-giving properties hangs by a delicate thread. They are direct consequences of the strength of the electromagnetic force and the specific geometry of the hydrogen bond. If the electrical attraction between the hydrogen and oxygen atoms in a water molecule were even slightly different, the entire suite of properties would collapse. If the hydrogen bond were a little stronger, water might become a rigid, gel-like substance at room temperature. If it were a little weaker, water would vaporize far too easily, and Earth's oceans would have boiled away into space eons ago. We find ourselves in a second, chemical layer of the fine-tuning puzzle. It is not enough that the universe forged carbon in stellar furnaces. That carbon must then find itself in a world bathed in a liquid with just the right set of bizarre, counterintuitive traits to allow chemistry to become biology. This brings the argument from the vastness of interstellar space directly to our own kitchen tap. The fine-tuning for life is not a distant, abstract concept about cosmological constants. It is written into the very substance that makes up most of our bodies and shapes the surface of our world, a daily, tangible reminder that the conditions for our existence are woven into the fabric of reality at every scale. Our world's rare chemistry is matched by an equally rare location in the cosmos. Earth does not merely exist in a habitable zone around its star. It occupies a profound sweet spot that seems almost too good to be true. Begin with our Sun, a remarkably stable, middle-aged star. Unlike the chaotic, flaring red dwarfs or the short-lived, brilliant blue giants, our Sun provides a steady, gentle flow of energy for billions of years. This consistency is the bedrock upon which the slow, gradual evolution of complex life is built. A single massive solar flare from a less stable star could strip a planet's atmosphere away, ending the story before it truly begins. Then there is our Moon, so familiar in our night sky. Its significance is staggering. It is far larger, relative to its planet, than any other moon in our solar system. This bulk gives it the gravitational influence to act as a steadying hand on the spinning Earth. Without our large moon, Earth's axial tilt would wobble chaotically over time. Imagine a world where the poles could suddenly shift to the equator, causing catastrophic, unpredictable climate swings every few million years. Such instability would likely prevent the long-term, stable ecosystems necessary for advanced life to develop and diversify. Our moon provides a gentle, consistent rhythm to the seasons, a metronome for evolution. Beneath our feet, another invisible shield protects the delicate story of life. Earth's molten iron core churns, generating a powerful magnetic field that extends far out into space. This magnetic bubble deflects the constant, lethal barrage of charged particles streaming from the sun, what we call the solar wind. Without this shield, this relentless assault would slowly but surely erode our atmosphere, stripping away the very air we breathe and exposing the surface to harmful radiation. Mars, which lost its global magnetic field long ago, stands as a silent testament to this fate. A dry and barren world where the atmosphere was gradually torn away by the solar wind. Further out in our solar system, another giant guardian watches over us. The planet Jupiter, with its immense gravitational pull, acts as a cosmic vacuum cleaner. It deflects or captures countless comets and asteroids that would otherwise hurtle inward toward the inner planets. While it does not catch every impact, as our planet's history of past extinction events shows, Jupiter drastically reduces the frequency of civilization-ending collisions. It provides a measure of long-term peace, a stable stage upon which life's long drama can unfold without constant, catastrophic interruption. Yet our privileged position extends beyond our solar system. We reside in a quiet suburb of our galaxy, the Milky Way, within what astronomers call the galactic habitable zone, too close to the chaotic, dense galactic center, and the radiation from countless stars and potential supernova would be overwhelming. Too far out in the sparse galactic outskirts, and there would not have been enough heavy elements forged in earlier generations of stars to form rocky planets like Earth in the first place. We are in the just right place, a peaceful neighborhood with enough building material for planets, but without the constant celestial violence of the inner galactic city. This convergence of factors, a stable star, a stabilizing moon, a protective magnetic field, a planetary guardian, and a safe galactic neighborhood paints a picture of a planet that is not just accidentally habitable, but remarkably, intricately suited for the flourishing of complex, long-lived life. But the argument goes one step further into a truly fascinating correlation. These same conditions that make Earth so hospitable also make it an unparalleled platform for scientific discovery. Our clear atmosphere allows us to see the cosmos. Our position in the galaxy gives us a clear view of its structure. The very stability that allows life to evolve also allows those living minds to observe, measure, and deduce the laws of the universe over generations. It is as if the universe is not only fit for life, but is also arranged in such a way that the life within it can come to understand its own home. This idea suggests a double gift, a world fine-tuned not just for existence but for exploration and comprehension. This progression from simplicity to staggering complexity is not a random accident. It appears to be written into the very rules of reality. The universe began as a near-uniform soup of energy and particles, a state of almost pure simplicity. Yet the laws governed by those finely tuned constants contained a hidden potential, a set of instructions for building up. Gravity pulled matter into clouds which collapsed into stars. Stars then forged heavier elements in their cores, and in their dramatic final acts, scattered those elements across space. Those elements became the raw material for rocky planets, for oceans, and for chemistry complex enough to form the first self-replicating molecules. This is a story of increasing order and information, a cosmic learning curve where the universe, in a sense, teaches itself how to build more intricate things. The physicist Paul Davies describes our physical laws as curiously bio-friendly. They do not merely permit life as a rare fluke, he suggests, but they actively encourage the rise of complexity and organization over vast stretches of time. Think of it like a river finding its way to the sea. The landscape of physical law is shaped in such a way that the natural flow of energy and matter tends toward the formation of islands of intricate order. The constants are the bedrock of that landscape, ensuring that matter can coalesce into stable, long-lasting structures. Atoms form molecules, molecules form crystals and cells, cells form organisms, and organisms eventually form networks of communication and thought. Each step represents a leap in the ability to store and process information. The DNA in every cell is a dense molecular library. A human brain is a vast living computer. The silicon chips in our devices are a continuation of this same cosmic trend, using the stable properties of matter to manipulate information in new ways. This view reframes the entire fine-tuning discussion. It is not just about a one-time, perfect setup at the moment of the Big Bang, like winding up a clock and letting it tick. It is about a dynamic enablement, a universe whose foundational laws contain the seeds of their own unfolding creativity. The fine-tuning allows for a cosmos that can evolve, that can learn, and that can ultimately become aware of itself. We are not passive inhabitants of a static, lifeless machine. we may be participants in a grand, generative process that was latent in the numbers from the very first moment. The mystery then deepens from why the numbers are right to why the rules they create tell such an elaborate and open-ended story. But what if this entire generative process, from the first particle to the human mind, is not running on cosmic hardware, but on something else entirely? A technological interpretation of our finely tuned reality has gained remarkable traction, one that reimagines the designer not as a divine being, but as a programmer. This is the simulation hypothesis. It proposes that our universe, with all its apparent laws and constants, is not the base level of reality. Instead, it is an immensely sophisticated digital construct, a simulation running on the unfathomable computer of a super-advanced civilization. In this view, the gravitational constant, the speed of light, the strength of nuclear forces, these are not fundamental truths of nature. They are simply the chosen parameters in the code, the settings selected by the creators of the simulation. The fine-tuning we observe would then be a form of engineering, but of a virtual reality, not a physical one. The philosopher Nick Bostrom formalized this idea into a compelling logical argument. He reasoned that if a civilization ever reaches a post-human stage capable of running vast, detailed simulations of conscious beings, and if they have any interest in doing so, then the number of simulated minds would quickly and vastly outnumber the minds in the original, base reality. Therefore, statistically speaking, any conscious being, like you or me, is far more likely to be living inside one of those countless simulations than in the lone original universe. It is a staggering piece of statistical reasoning that turns our intuition inside out. The hypothesis connects the mystery of fine-tuning directly to concepts in computer science and information theory. In a simulation, the laws of physics are the algorithms. The conservation of energy is a rule to prevent processing errors. The Planck length, the smallest possible unit of space, could be seen as the pixel size of the simulation's rendering engine. Even the weirdness of quantum mechanics, with its probabilities and observations, has been compared by some thinkers to the way a video game might only render the detailed properties of an object when a player is looking at it, to save on computational power. This is, of course, profoundly speculative and currently untestable, but as a thought experiment, its power is undeniable. It offers a purely technological, naturalistic explanation for a designed-seeming cosmos, one that requires no supernatural entities. It simply shifts the origin story one level up to programmers in a higher reality whose own origins remain unexplained. The simulation hypothesis ultimately does something more profound than provide an answer. It fundamentally challenges our conception of what is real. If this is a simulation, then the quest for a fundamental theory of everything in physics becomes the quest to reverse engineer the source code. Our awe at the mathematical elegance of the universe becomes an appreciation for elegant programming, and our search for meaning takes on a new dimension, pondering not why we are here, but what the purpose of the simulation might be. Are we ancestors in a historical archive, characters in an entertainment, or subjects in a cosmic experiment? The silence of the cosmos, the Fermi paradox we touched on earlier, could even be explained as a deliberate isolation of our simulation instance. This idea pushes the fine-tuning debate into the realm of the meta, forcing us to question the very ground of our existence, all while keeping one foot firmly in the language of science and technology. Yet this dizzying idea of a programmed cosmos brings us back to a tangible, undeniable reality, the very one reading these words. Your own existence is the product of a different, but no less profound kind of fine-tuning, one written not in the laws of physics, but in the language of biology. The same question of a just right setup echoes from the cosmic scale down to the microscopic world of the cell. Consider the leap from non-living chemistry to the first living organism, a process scientists call abiogenesis. For life to begin, a staggering number of conditions had to align on the early Earth. The right mix of chemicals in the right concentrations, with a reliable energy source like sunlight or geothermal heat, all within a protective environment, perhaps near a deep-sea vent or within a clay bed. The probability of these ingredients spontaneously assembling into a self-replicating system, even over millions of years, strikes many as astronomically low, another layer of apparent fine-tuning. Then there is the molecule of life itself, deoxyribonucleic acid. DNA functions as an intricate information storage system, a digital code written in a 4-letter chemical alphabet. The precise sequence of these letters in your genome carries the instructions to build and maintain your entire body. The sheer density and specificity of this information, far exceeding any human-designed software, raises a compelling question for some. Can undirected chemical processes alone produce such complex, specified information, or does it point toward an intelligent source? Proponents of intelligent design often highlight structures within the cell they call irreducibly complex. These are molecular machines like the tiny flagellar motor that some bacteria use to swim. This motor is a miniature outboard engine complete with a rotor, a stator, and a propeller. The argument suggests that if you remove any one of its dozens of protein parts, the entire motor ceases to function. It could not have evolved step by step, they argue, because the intermediate, incomplete versions would offer no survival advantage. It appears to be a system that only works when all its components are present and assembled, a biological watch that seems to demand a watchmaker. It is crucial to present the robust scientific response to these points. The field of origins of life research is actively exploring how natural processes could bridge that gap from chemistry to biology. Experiments have shown that many building blocks of life, like amino acids, form readily under conditions simulating the early Earth. Scientists are investigating how simple RNA molecules might have been able to both store information and catalyze their own replication, a potential precursor to DNA-based life. Regarding irreducible complexity, evolutionary biologists demonstrate how complex systems can indeed arise from simpler parts that originally served different functions. A component used for one job can be copied and co-opted for a new role, gradually assembling into a more complex machine over vast stretches of time. The bacterial flagellum itself may have evolved from a simpler structure used for secreting proteins. This ongoing research does not yet have all the answers, and the origin of life remains one of science's great unsolved mysteries. But it provides a naturalistic framework for investigation, showing that biological fine-tuning might be the result of emergent complexity over deep time, rather than a single miraculous setup. Whether one looks through the telescope at the fine-tuned constants of the cosmos, or through the microscope at the intricate machinery of the cell, a similar sense of awe and mystery emerges. The patterns resonate across scales, suggesting that the question of purpose, chance, or design is not confined to the moment of the Big Bang, but is woven into the very fabric of reality, from the largest galaxy to the smallest strand of DNA. This bridge between the cosmic and the biological deepens the puzzle, inviting us to wonder if the universe's apparent fine-tuning was all leading up to this moment of conscious reflection. But this intricate, seemingly purposeful cosmos presents us with a profound and unsettling contradiction. A universe exquisitely tuned for life is also a universe filled with immense suffering and apparent waste. This is the classic problem of evil, and it stands as the most significant counter-argument to the idea of a benevolent designer. If the cosmos was engineered for us, why does it so often feel hostile to life's well-being? Look out into the vastness of space itself. The overwhelming majority of our universe is a lethal vacuum, bathed in radiation, dotted with exploding stars and crushing gravitational fields. Our own solar system, beyond the thin, green band of Earth, is a collection of frozen rocks, toxic atmospheres, and barren giants. This cosmic real estate is overwhelmingly inhospitable, a fact that seems at odds with a universe purpose built for living inhabitants. Our planet's own history is a chronicle of violence and loss. Geological records tell of at least 5 major extinction events, moments where the global environment changed catastrophically. The most famous, the event that ended the age of dinosaurs, was likely caused by an asteroid impact, a random piece of cosmic debris that wiped out most life on Earth. Beyond these cataclysms, nature operates with a stark indifference. Earthquakes, tsunamis, and pandemics claim lives without regard for morality or innocence. The natural world is built on cycles of predation and competition, where survival often comes at the expense of another creature's suffering. This reality forces a difficult question. Can we reconcile the image of a fine-tuning watchmaker with a world that contains childhood illness, genetic disorders, and the relentless march of decay that affects all living things? Those who argue for design offer several responses. Some suggest that a universe with stable, predictable laws of physics, which allows for life, must also allow for natural disasters. You cannot have the tectonic plates that recycle nutrients and build continents without also having the potential for earthquakes. You cannot have a dynamic atmosphere that distributes heat and fresh water without also creating hurricanes. In this view, the so-called evil is a necessary byproduct of a system that is, on the whole, good and life-permitting. Others propose a soul-making theodicy. They argue that a world without challenge, risk, or hardship would be a world without courage, compassion, innovation, or love. The very virtues we cherish are forged in response to difficulty. A perfectly safe, pain-free garden might not allow for the growth of character or the depth of human experience. From this perspective, the universe's apparent imperfections are not evidence against a designer, but essential ingredients in a grand, inscrutable plan for the development of conscious, moral beings. Skeptics find these explanations deeply unsatisfying. They point to the sheer scale and randomness of the suffering. Was the asteroid that killed the dinosaurs necessary for moral growth? Is the genetic mutation that causes a lifetime of pain a meaningful character-building exercise for an infant? To many, the problem of evil suggests a simpler, if colder, answer. The universe is not fine-tuned with benevolent intent. It is simply a physical system that, through a staggering combination of luck and the multiverse, produced a rare oasis where life emerged. And life, through the blind process of evolution, is inherently accompanied by struggle and suffering. The universe is not hostile or benevolent, it is indifferent. Engaging with this tension is not a distraction from the fine-tuning debate. It is its necessary counterpart. Any honest exploration must stare directly into this paradox, acknowledging that the cosmos gifts us with both the sublime beauty of a nebula and the terrifying power of a supernova. It gives us the capacity for profound love and the reality of profound loss. The problem of evil does not dissolve the mystery of fine-tuning, but it deepens it, framing our cosmic story not as a simple tale of purpose, but as an infinitely complex narrative of both harmony and discord, leaving us to wonder what, if anything, it all means. This profound silence from the stars presents us with a direct and unsettling test. The search for extraterrestrial intelligence, or SETI, has for decades pointed its radio telescopes at the cosmos, listening for any pattern, any signal that would break the quiet. So far, the result has been a vast and unbroken silence. This absence is formalized in what we call the Fermi paradox, named for physicist Enrico Fermi, who famously asked a simple, devastating question during a lunchtime conversation. If the universe is so old and so vast, with billions of planets that could support life, then where is everybody? Why haven't we seen any evidence, any artifacts, or any signals? This paradox cuts to the heart of the fine-tuning mystery. If the universe's constants are so perfectly set for life, then life should, in some form, be a common cosmic outcome. The silence suggests otherwise. It hints that the chain of events leading from a lifeless planet to a technological civilization might be unimaginably fragile, a series of lucky breaks where any single link could fail. Perhaps life itself is rare, or perhaps life emerges but intelligence is a fluke, or perhaps civilizations inevitably face a great filter, some catastrophic event or technological trap that prevents them from reaching the stars and making their presence known. Each of these possibilities reshapes the fine-tuning argument. If we are alone, then Earth is not just a rare planet. It is a statistical miracle, a one-in-a-trillion occurrence that happened against all odds in a universe mostly hostile to complex beings. This profound isolation could be seen as the ultimate form of fine-tuning, where the entire cosmos was calibrated to produce this one singular experiment in consciousness. It lends weight to the idea of a special purpose, a garden cultivated in a silent desert. On the other hand, if we were to discover even a single instance of microbial life elsewhere, like on Mars or in the subsurface ocean of Jupiter's moon Europa, the implications would be staggering. It would suggest that the step from non-living chemistry to living organism is not a miraculous barrier, but a natural, almost inevitable process in the right conditions. This would make the universe seem inherently bio-friendly, tilting the scales toward the multiverse or naturalistic explanations. The constants would be seen as permitting life as a common feature, not a singular event. Our ongoing study of exoplanets adds fascinating layers to this test. We now know that planets are not rare. Our galaxy alone likely contains billions of them, many in the so-called habitable zone where liquid water could exist. But habitability is a broad concept. A planet can be in the right place and still be a toxic, volcanic, or tidally locked world utterly unlike Earth. The fine-tuning for complex life, as we discussed earlier, involves a much narrower set of requirements: a stable star, a protective magnetic field, a large stabilizing moon, the right atmospheric composition. Finding another Earth-like world, a true analog, remains a monumental challenge. The continued silence, combined with our growing catalogue of diverse and often hostile worlds, makes our own blue marble seem more and more exceptional. This leaves us in a state of suspended judgment, listening to a quiet that is either deeply meaningful or merely empty. The search itself, however, is a testament to the very fine-tuning we are trying to understand. It is only because the universe is orderly, measurable, and consistent that we can point our instruments at distant stars and hope to understand them. The quest for an answer continues, and the outcome, whether a signal or a lasting silence, will forever alter how we see our place in this finely tuned cosmos. This profound silence might be telling us something deeper than we first realize. It forces us to confront a humbling possibility. What if the fine-tuning problem is not a puzzle to be solved, but a mirror reflecting the limits of our own minds? Our brains are magnificent pattern recognition engines, forged by evolution to find causes in the rustling grass, to see agency in the shifting shadows. This instinct kept our ancestors alive, but it may also predispose us to a certain kind of error when we look at the cosmos. We are wired to ask why, and to expect an answer in terms of intention or mechanism. But the ultimate nature of reality may not fit into either of those familiar boxes. Philosopher Thomas Nagel has explored this idea of cognitive closure, the notion that some truths about the universe might be permanently beyond the grasp of a human intellect, just as the concept of calculus is forever beyond the understanding of a chimpanzee. Our mental machinery, for all its power, evolved to navigate a middle world of medium-sized objects moving at modest speeds. It was not built to intuitively grasp the quantum vacuum or the geometry of 11-dimensional space. So when we stare at the exquisitely set constants and feel a sense of awe or suspicion, we must ask ourselves, are we perceiving a genuine signature of mind, or are we simply projecting our own cognitive habits onto a reality that operates on principles fundamentally foreign to us? The question, why is there something rather than nothing, may be the ultimate example. It feels like a valid, even necessary question, but it assumes that nothingness is a default state from which something must have emerged. Yet our best physics suggests that a true, stable nothing, a complete absence of space, time, and physical law, may not even be a coherent concept. The fine-tuning problem, then, could be a signpost pointing not toward an answer, but toward the boundary of our current conceptual map. It invites a fundamental rethinking of our approach. Instead of demanding a cause, we might need to learn a new way of thinking altogether, one that can accommodate a universe where the most foundational facts are simply and beautifully given. This is not a surrender, but a call for a different kind of humility and a broader imagination. Our instinct to see order in the cosmos is as ancient as humanity itself. Long before we had the equations of physics, cultures across the globe looked up at the regular motions of the stars and the changing of the seasons and perceived a profound harmony, a governing principle behind the chaos of the world. In ancient Egypt, this was known as Maat. It was more than just a goddess. It was the fundamental concept of truth, balance, and cosmic order that held the universe together. Maat was the force that ensured the sun would rise, the Nile would flood, and justice would prevail in society. To live in accordance with Maat was to align oneself with the very structure of reality. Across the world, in the ancient Vedic traditions of India, a remarkably similar concept emerged called RTA. This was the eternal, rhythmic order embedded in nature, the principle behind the regularity of day and night, the cycles of birth and decay, and the moral law of the universe. For these cultures, the cosmos was not a random accident. It was a living, ordered system with an inherent ethical dimension. The physical laws and the moral laws were seen as two expressions of the same foundational truth. Jumping forward and looking at the Abrahamic traditions, we find a different but related framework. Here, the order of the cosmos is understood as the product of a divine intellect, a creator who establishes immutable laws of nature. The book of Genesis speaks of a God who separates the light from the darkness and sets the celestial bodies in their courses, a narrative of intentional structuring. For medieval scholars like Thomas Aquinas, the magnificent regularity of the natural world, what he called the eternal law, was a direct reflection of divine reason, a readable book that pointed toward its author. This idea laid crucial groundwork for the later scientific revolution, as it fostered a belief that the universe operated according to consistent, discoverable rules. What is so fascinating is that these diverse interpretations, separated by vast distances and millennia, all spring from the same human experience, the awe of a universe that appears to follow a script. The modern fine-tuning argument, with its precise mathematical constants, is in many ways the latest chapter in this enduring story. It translates that ancient intuition of cosmic harmony into the precise language of physics. When a physicist notes that the strength of gravity is calibrated to 1 part in many millions, they are expressing a quantitative version of that same wonder felt by an Egyptian priest observing the predictable path of a star. Understanding this deep historical context does not prove any one interpretation correct, but it does something vital. It reframes the debate. It reminds us that we are not the first to ask these questions. We are participants in a conversation that spans cultures and centuries, a conversation about whether the stunning order we perceive is a silent, mechanical given, or a meaningful signal waiting to be understood. This long human conversation enriches our modern puzzling, connecting our equations to a lineage of wonder that stretches back to the very dawn of human curiosity. These ancient intuitions of cosmic order now find a startlingly precise voice in modern mathematics. To move from a feeling of wonder to a concrete argument, we must ask a brutally simple question: just how special is our universe? Physicists approach this by trying to quantify the tuning. They take a fundamental constant, like the strength of gravity or the amount of dark energy, and ask, within what range could this number sit and still allow for a universe that could eventually host life? The answer for many of these constants is a range so narrow it defies everyday comprehension. Take the cosmological constant, the energy of empty space driving the universe's expansion. The theoretical range of possible values based on our best physics is enormous, spanning over 120 orders of magnitude. That is a 1 followed by 120 zeros. Yet the actual observed value that allows for galaxies, stars, and planets to form sits in an almost unimaginably tiny sliver of that vast landscape. The life-permitting window is so small that it has been compared to the odds of throwing a dart blindfolded across the entire observable universe and hitting a bull's-eye no larger than a single proton. That is not a metaphor for extreme difficulty, it is a numerical reality. The same kind of analysis applies to other constants. The initial conditions of the Big Bang, the ratio of the strengths of the fundamental forces, the mass of the electron, each one appears dialed in with a precision that echoes this theme of breathtaking improbability. When you multiply these individual improbabilities together, the odds of getting a universe like ours by random chance become so astronomically small that the number is essentially meaningless to the human mind. It suggests that a universe capable of crafting conscious beings is not a common or easy outcome, but an exception of staggering rarity. This is the mathematical heart of the fine-tuning argument, transforming a philosophical hunch into a series of equations that whisper of a cosmic lottery with odds beyond calculation. Yet we must pause here. These probability calculations rest on a critical and often unspoken assumption that every possible value across that gigantic theoretical range was equally likely to occur. We are assuming the cosmic dials could have been spun freely and randomly, but what if they could not? What if a deeper yet undiscovered law of physics determines these values, making them inevitable, not accidental? The debate over fine-tuning is, in many ways, a debate over this very premise. Are we calculating the odds of a truly random draw, or are we mistakenly treating fixed features of reality as if they were lottery numbers? The mathematics of improbability gives the fine-tuning argument its formidable weight, but it also reveals where the ground beneath our feet is still shifting, waiting for a deeper theory to tell us what was truly possible at the dawn of everything. That staggering improbability rests on a fragile hope that our current physics is incomplete. For many researchers, the fine-tuning problem is not a mystery to be solved by philosophy, but a signpost pointing toward a deeper level of reality. Their dream is a final theory of everything, a single, elegant framework that unifies all forces and particles. In this vision, the constants we see are not 26 independent dials that could have been set anywhere. They are more like the notes in a symphony, inevitable outcomes flowing from the structure of the score itself. The strength of gravity, the mass of an electron, the cosmological constant, all would emerge as necessary mathematical consequences, just as the value of pi emerges from the geometry of a circle. The universe would be the only universe it could possibly be. The apparent fine-tuning would simply vanish, explained away by a deeper, more beautiful law. This is the driving force behind pursuits like string theory, with its tiny vibrating strands of energy, or loop quantum gravity, with its woven fabric of space-time. These are attempts to find that master equation, a mathematical key that locks the constants into place. The quest itself is a testament to science's faith that beneath apparent complexity lies profound simplicity. Yet, even if this dream is realized, a haunting question remains. Would the master equation itself be fine-tuned? Imagine we finally discover the ultimate theory, a concise set of principles scribbled on a single page. Those principles would have certain mathematical properties. They would allow for rich, complex structures to emerge over time. They would permit stability and novelty, chemistry and consciousness. In other words, the laws themselves would be bio-friendly, mathematically fertile in a very specific way. We could then ask, why this particular set of laws? Why a mathematical structure that allows for a universe to know itself? The mystery would not disappear. It would simply shift to a new, more fundamental level. Instead of asking why the constants are just right, we would ask why the foundational law is just right. The search for a deeper explanation might lead us right back to the same set of choices: staggering mathematical luck, a multiverse of possible laws, or a reason woven into the fabric of logic itself. The fine-tuning problem, it seems, is a relentless companion, always waiting at the next frontier of understanding. The equations and arguments we have explored are not just abstract puzzles. They are mirrors reflecting back a question about our own place in the story. Stepping back from the physics, what does this cosmic fine-tuning actually mean for you, sitting here in this moment? This is where the data transforms into a personal experience. For some, the staggering improbability of our universe sparks a deep and quiet awe. It is the feeling of looking up at a clear night sky and realizing that every star, every atom in your hand, exists because of a chain of perfect conditions stretching back to the first instant of time. You are not just a passive observer, you are a testament to an epic sequence of events so precise it defies belief. That awareness can instill a profound sense of gratitude for the simple fact of being here at all. For others, the same data might evoke a different feeling, a sense of cosmic loneliness. If our universe is so uniquely tuned, then the vast, silent stretches of space between galaxies feel even more immense and empty. The thought that we might be a solitary, fragile island of meaning in a silent void can be a humbling, even sobering realization. It places a weighty responsibility on our shared existence. Then there is the perspective of purpose. The apparent design, whether through a multiverse or something else, can feel like an invitation. It suggests that the universe is not merely a chaotic accident, but an arena where life and mind are not just possible, but perhaps a meaningful part of its unfolding narrative. Your curiosity, your capacity for love and wonder, might be features of the cosmos becoming aware of itself. And of course, for many, the only honest response is a deepened curiosity. The mystery does not demand a final answer, but rewards the act of questioning itself. It transforms the universe from a static backdrop into an active riddle, encouraging a lifetime of learning and exploration. There is no single correct emotional response to this information. Your reaction is woven from your own experiences, your values, and your way of seeing the world. The true power of the fine-tuning problem may lie not in forcing a conclusion, but in how it reshapes the questions we carry with us every day. It asks us to consider what kind of universe we believe we live in, and in turn, how we choose to live within it. Yet for every compelling argument, there exists an equally compelling counterpoint. To see the full picture, we must hold these skeptical views up to the light. The first is perhaps the simplest to state, but the most difficult to truly accept. It is the stance of cosmic luck. In this view, our universe is a statistical fluke of unimaginable proportions, a one in a number so large it has no name. We are the winners of the ultimate lottery, holding the single golden ticket in an infinite cosmic drawing where every other ticket leads to nothingness. Proponents argue that while the odds are astronomically small, they are not zero. Given enough time or enough possible starting points, even the most unlikely event must happen somewhere, sometime. We just happen to be the somewhere. This position asks us to accept a miracle of chance, but it does so without invoking any entities or unseen realities beyond our own. Then we have the multiverse solution, which we have explored. This framework attempts to dissolve the improbability by multiplying the arenas in which chance can operate. If there are an infinite number of universes or a near infinite number, each with randomly dialed constants, then it becomes a mathematical certainty that at least one will have the right combination for life. We, by necessity, find ourselves within that one. It is a powerful idea that shifts the question from why this universe is tuned for life to why we observe a universe tuned for life. The critique, of course, is that it moves the goalposts. It explains our local fine-tuning by positing an unimaginably vaster and more complex reality for which we have, as yet, no direct evidence. Some see it as a brilliant escape from a theological conclusion, while others see it as replacing one mystery with an even grander one. A third skeptical position comes from within the heart of science itself. It is the argument from incomplete knowledge. Physicists critical of fine-tuning often point out that our current models are almost certainly not the final word. We have two towering theories, general relativity and quantum mechanics, that do not yet fit together. The constants we see as independent knobs may, in a future theory of everything, turn out to be locked together, the inevitable outcome of a single, elegant master equation. In this view, the universe could not have been any other way. The appearance of choice of dials that could have been set differently is an illusion created by our partial understanding. We are like someone who finds a perfectly crafted key and marvels at the odds it fits a specific lock, not realizing that the lock was built around the key all along. Finally, we must consider the perspective from within our own minds. This is the argument from cognitive bias, the illusion of design. Human brains are exquisitely tuned pattern recognition machines. We see faces in clouds, hear words in random noise, and infer intention behind chance events. This skill kept our ancestors alive, but it can also lead us astray. Skeptics suggest that the fine-tuning argument is a grand, cosmic example of this tendency. We have looked at the universe, found it compatible with our existence, and instinctively inferred a cause that fits our human-scale understanding of creation. We are asking a question loaded with our own cognitive biases, and then marveling at the answer that seems to confirm them. The universe is not fine-tuned for life, this view holds. Life is simply a phenomenon that emerged within the narrow band of conditions this particular universe happens to have. We are the product of the laws, not the purpose behind them. Holding all four of these positions together is essential. They remind us that the data, while startling, does not speak with a single voice. Fine-tuning is not a closed case in the scientific community, but an open and vibrant debate. It is a profound puzzle where the evidence points insistently toward something extraordinary, yet the interpretations of that something diverge dramatically. Recognizing this complexity is not a weakness, but the very strength of the scientific and philosophical inquiry. It means the conversation is alive and that our understanding is still evolving. Standing at this crossroads of interpretation, we find ourselves holding not a single thread, but a whole tapestry of interconnected wonders. The fine-tuning problem is not merely a list of improbable numbers. It is the gravitational constant that allows stars to burn for billions of years. It is the precise nuclear resonance that fills the cosmos with carbon. It is the unique expansion rate that gave galaxies room to breathe, and the anomalous properties of water that fill a living cell. Each thread, from the cosmic to the biological, is woven into the same grand and perplexing pattern. This pattern does not speak in a single language. It whispers in the mathematics of physics, it echoes in the logical structures of philosophy, and it shouts in the visceral reality of our own conscious existence. Here, at this unique intersection, the quantitative data of science meets the qualitative hunger for meaning that has defined humanity since we first looked up at the stars. The universe presents us with a set of facts so precise they seem curated, yet it does not hand us the manual to explain why. This forces a kind of intellectual humility. The data itself does not force a conclusion. Instead, it illuminates the landscape of profound choices we each must navigate in our attempt to interpret reality. To choose the multiverse is to embrace a reality of unimaginable scope, where our existence is both statistically inevitable and cosmically lonely. To see a miracle is to perceive a signature in the fabric of space and time, a hint of purpose written into the laws themselves. To sit with the mystery is to acknowledge the limits of our current understanding, to find a kind of awe in not knowing. Each path is a valid response to the same evidence, a different way of weaving the threads into a coherent story. What becomes clear is that our universe, by any measure, is exceptionally arranged for the emergence of complexity, consciousness, and curiosity. This recognition is the true gift of the fine-tuning problem. It prepares the ground not for a final answer, but for a deeper kind of questioning. The value lies less in which interpretation we tentatively choose, and more in the fact that we are compelled to choose at all. We are beings capable of being stunned by the universe that made us. In that stunned silence between the data and the wonder, the real journey begins. So we have traversed the cosmos, from the fiery hearts of newborn stars down to the quantum dance within a single atom, all to confront one staggering question. Is the universe engineered for life? The evidence laid before us is undeniably compelling. The numbers are etched into reality with a precision that defies casual explanation. Yet the interpretations of this data remain deeply, perhaps permanently, divided. You may find yourself drawn to the vast and silent architecture of the multiverse, a cosmic landscape where every possibility blooms. You might feel the pull of a deeper order, a signature of mind or purpose written into the fabric of space and time itself. Or perhaps you stand in sheer awe of the staggering, beautiful accident that our existence represents, a cosmic lottery won against impossible odds. Wherever you land, this mystery extends an invitation. It asks us to live with a profound and abiding sense of wonder, not just at the universe, but at the simple, staggering fact that we are here at all. We are conscious beings born from stardust, living on a pale blue dot, in a universe that is somehow structured to allow us to ponder its own existence. The astronomer Carl Sagan once reflected that we are a way for the cosmos to know itself. In that light, fine-tuning is not a puzzle to be solved so much as a relationship to be acknowledged. We are not separate from the universe, studying it from a distance. We are the universe studying itself. This realization can be the beginning of a deeper curiosity, not its end. We want to hear where this journey has taken you. Share your thoughts in the comments below. Which interpretation of the fine-tuning problem resonates most deeply with you, and why? If you enjoyed this exploration to the very edge of understanding, please consider subscribing. We have many more deep dives into the universe's greatest mysteries waiting for you. Thank you for watching, and keep looking up.